All right, let's dive right in. Welcome to this explainer. I am thrilled to have you here. Today, we're taking a high-stakes tour into a world you probably rarely see, but honestly, you rely on it every single day. We're talking about the hidden, rigorously structured protocols that keep the world safe from microscopic threats. Microbial research is the absolute backbone of modern biotechnology, medicine, and agriculture. But with great science comes immense responsibility. We're going to break down the exact guidelines, the armor, and the procedures scientists use to handle the absolute most dangerous pathogens on Earth. So consider this your official lab safety briefing. Today we're covering the invisible laboratory threat, leveling up through the biosafety tiers, the scientists' armor and tools, sterilization and waste management, surviving emergencies and spills, and finally, biosecurity and the future. Let's get to it. Section 1. The invisible laboratory threat. Microorganisms are essentially the engine of modern biotech. But because they're invisible, handling them poses a very real, very tangible risk to personnel, the public, and the environment. That brings us to this definition directly from the World Health Organization. Biosafety is defined as the containment principles, technologies, and practices implemented to prevent unintentional exposure to biological agents and toxins or their accidental release. I want you to really focus on those words for a second: containment, principles, and technologies. Biosafety isn't just bureaucratic red tape or a checklist on a clipboard. It is a highly engineered, deeply physical barrier designed to keep the invisible, dangerous stuff in and vulnerable human beings out. So why does this matter to you and me? Well, the stakes are absolutely massive. These rules are literally the invisible walls standing between a contained, controlled laboratory experiment and a devastating community outbreak. Good biosafety practices protect the lab personnel doing the gritty work, they prevent laboratory-acquired infections, and they protect the environment from accidental release. They also ensure we're safely handling genetically modified organisms, or GMOs. Ultimately, these protocols are exactly what maintains public health and safety on a global scale. Section 2. Leveling up. Biosafety tiers. Okay, so not all microbes are created equal, right? The scientific community uses a really rigorous tier system based on risk assessment, categorizing microorganisms into 4 risk groups that map directly to 4 biosafety levels, or BSLs. Down at risk group 1, or BSL1, the risk is minimal. We're talking things highly unlikely to cause disease in healthy humans, like lactobacillus, the friendly bacteria in your yogurt. You can work with those on an open bench in a standard lab coat. But man, look at how the danger scales up. By BSL2, you've got moderate individual risk with pathogens like Salmonella. Hit BSL3 and things get deadly serious. We're talking high individual risk and serious disease potential, like tuberculosis, requiring negative air pressure and HEPA filters. And then we hit BSL4. Severe disease, high mortality, and critically, no effective treatment available. Pathogens like the Ebola and Marburg viruses. When you're dealing with a risk group 4 pathogen, the protocol goes to the absolute extreme. BSL4 laboratories represent maximum containment. Scientists literally have to wear full-body positive pressure suits with dedicated air supply systems. It looks like a futuristic spacesuit, and that's kind of exactly what it is. It's a personal, wearable spaceship protecting the scientist from a microscopic environment where a single mistake can be fatal. Because remember, for BSL4 agents, there is no cure. Section 3. The scientist's armor and tools. So how do researchers actually physically shield themselves from these escalating threats? The crucial point here is understanding the difference between the 2 main types of containment. Primary containment is all about protecting the laboratory personnel directly at the bench. This is your immediate armor: gloves, face shields, respirators, and biosafety cabinets. Secondary containment, on the flip side, is about protecting the external environment and the community outside the lab. This stuff is baked right into the architecture of the building itself. We're talking specialized lab design, controlled access doors, advanced ventilation systems, and dedicated waste treatment facilities. Simply put, primary protects the scientist, secondary protects the world. The ultimate piece of primary containment armor is the Biological Safety Cabinet, or BSC. These are specialized workspaces designed specifically to protect against infectious aerosols. A Class 1 cabinet protects the personnel and the environment, but it actually doesn't protect the product being worked on. Class 2 is the real workhorse. It's the most commonly used in microbiology labs because it protects the personnel, the environment, and keeps the biological product itself uncontaminated. And finally, Class 3 is the absolute maximum containment cabinet. It is completely enclosed, totally gas-tight, and strictly reserved for those terrifying BSL-4 highly infectious pathogens we talked about earlier. Section 4. Sterilization and Waste Management. Okay, once an experiment is done, how do scientists ensure these microscopic threats don't just make it out to the local landfill? They use incredibly methodical physical protocols to neutralize them completely. 121. That number is practically legendary in a microbiology lab. It stands for 121 degrees Celsius. To achieve true sterilization, which means the absolute complete destruction of all microorganisms, including really tough spores, laboratories use a physical method called autoclaving. An autoclave blasts high-pressure steam at 121 degrees Celsius and 15 psi for about 15 to 20 minutes. It's essentially a giant high-tech pressure cooker that guarantees absolutely no biological material survives. It is the ultimate reset button for contaminated glassware and culture media. But you can't exactly fit a whole laboratory bench into an autoclave. For that, we rely on disinfection, which knocks the microbial load down to safe levels. We use a few common chemical weapons for this every single day. 70% ethanol is great for routine surface wipe downs. Sodium hypochlorite, which is really just bleach, is heavily used for liquid waste treatment before disposal. And phenol is an industrial strength cleaner used for broader lab surfaces. Literally every piece of disposable PPE, every sharp needle, and every culture has to meet these chemicals or an autoclave before it ever leaves the facility. Section 5. Surviving emergencies and spills. Even with all this cutting-edge armor and technology, human error and equipment failure are just realities. It's the exact question that keeps lab directors awake at night. What happens when containment fails? A glass flask drops, a needle slips, maybe an aerosol is generated outside a safety cabinet. In those split seconds, panic is totally off the table. Strict discipline is the only survival strategy. When a spill happens, scientists immediately execute a highly disciplined 6-step management procedure. First, evacuate the area immediately if necessary. Then, and this is incredibly crucial, you wait. You have to allow the infectious aerosols to settle. Rushing back in means breathing in the pathogen. Once everything is settled, scientists put on their PPE, gently cover the spill with absorbent material to prevent it from spreading further, and apply to correct chemical disinfectant. After giving it enough contact time to work, all that contaminated material is safely disposed of, usually straight into an autoclave bag. It is a highly calculated neutralization of a live threat. Section 6. Biosecurity and the future. Up until now, we've really only been talking about accidents. But what about intentional threats? And how is technology changing the landscape of lab safety? We really need to clarify two terms that get mixed up all the time: biosafety versus biosecurity. Biosafety is all about protection against accidental exposure. It's the gloves, the autoclaves, the spill protocols. Biosecurity, on the other hand, is protection against the intentional misuse of biological materials. Biosecurity measures include strict controlled access to facilities, intense inventory management of pathogen vials, personnel reliability programs, and highly secure storage. So basically, biosafety keeps the bug from accidentally escaping the lab. Biosecurity keeps a bad actor from intentionally walking out the front door with it. All of this builds into a massive, overlapping web of international and national regulations. The global landscape is heavily governed. You've got the WHO providing the foundational laboratory biosafety manual and the OECD outlining biotechnology safety guidelines. When we're talking about living modified organisms and protecting biodiversity, the Cartagena Protocol is the international standard. Zooming into a national level, countries have really strict frameworks. In India, for example, the Department of Biotechnology and committees like the GAAC rigorously review genetic engineering research, and they have to explicitly approve any environmental release of GMOs. It's an incredibly tight net of regulatory oversight. And a tech in this field is just advancing at lightning speed to meet new challenges. We're way past just relying on paper logs and simple air pressure gauges. Today, we're seeing the rise of digital biosafety monitoring with automated risk assessments. We're building smart biosafety laboratories equipped with real-time environmental monitoring and automated containment systems that can trigger the exact second a pressure drop is detected. And honestly, this is wild. We are now utilizing AI-based biosurveillance for early detection of biological hazards and enhanced outbreak monitoring. Technology is quickly becoming our ultimate secondary containment, which leaves us with this crucial thought. As genetic engineering and biotechnology keep advancing at lightning speed, creating both unprecedented medical breakthroughs and entirely novel risks, how do we stay one step ahead of the invisible threats? The answer lies in the rigorous, constantly evolving protocols we've explored today. It's a really delicate, highly engineered balance between pushing the boundaries of scientific progress and maintaining the invisible walls that keep humanity safe. Thank you so much for joining me on this explainer. Stay curious, stay focused, and I'll see you next time.